It's great pleasure to have Claire. I'm sorry, it's a great pleasure to have Claire Boyer here, and she's a professor at in the Department of Mathematics at the University Paris-Saclay, and also a junior member of the University Institute in France. And she has done a lot of work on various aspects of statistical machine learning, high-dimensional statistics, and related topics. Yeah, it's welcome, Claire.
Thank you for the invitation. I'm pleased to be here, and I'm glad to see you here while it's spring break, right? So today is about the work that we've done with Pierre-Marion, Raphaël, Bertie, and Gerardo, where we wanted to analyze the statistical abilities of attention layers, because in the literature, in the statistical learning literature, you can find a lot of analysis, but often they are focusing on approximation of properties or on particle systems, and not exactly explaining why attention layers are powerful in different and various statistical tasks. So, no, there are, I'm a bit going a bit too fast here. There are some works about in-context learning, of course, that are very interesting, but we wanted to actually find a statistical task that could be naturally solved by attention layer, and such that no other standard predictors could do it. So we come, after years of discussion, we come to the single location regression problem. So I will just introduce it to you. So we are in the case of the regression. So it means that we are doing supervised learning here. We have input and output, or output one be a scalar. But the input, we have a particular structure. So we will assume that we will have access to a sequence of tokens. Okay, XM. Okay. And so each token, so in this talk, I will make the confusion between token and words. Okay, this will be easier. Of course, in practice, tokens are shorter than words, but yeah, for the motivation and for the mathematical aspect, this is enough. So each token will be an RD vector, a d-dimensional vector. So it means that my pairs of variables are made of the output and a whole sequence of tokens of words. Okay. So to define the single location regression, I need to say how Y is linked to X. So we've been inspired by natural language processing problem, and we come to the following model. So maybe I will put it here to keep it. So we would assume that Y is formed as a linear combination of a particular token, xg0, against V star plus some noise. Okay? And G0 is just the index, a random index that is pointing out the relevant token in the input sequence. Okay? So J0 is a random variable on one.
Do we assume that L is fixed here?
Yes, L is fixed.
One question.
Yeah.
So are these tokens, like are they coming from a user network? Are they representations, or
I'm going to put a strong assumption on them right now. So to make the mathematical analysis, I need to put a distribution on my token. So the strong assumption are following. We will assume that conditionally on G0, xg0 is drawn according to a Gaussian that is centered along a direction k star, with here a scaling factor of d, square root of d, d is the dimension of the embedding, okay? Identity. Okay? And when I'm not a relevant token, I'm just, sorry, I should put here a gamma square. I'm just a standard Gaussian vector. Okay? So what does it mean? It means that if you give me the sentence, so this sequence of tokens, my relevant token is the one that is aligned with k star. And when I'm not a relevant token, I'm just centered at zero.
So this k star, where do you define it?
So k star is actually a parameter of my model. So here I should say I have two parameters in this model, k star and b star. And both I will assume that they live on the sphere. Okay, if I knew k star and b star, I could predict my y, right? Because I would just check the alignment of the token with k star that would give me the relevant token, and then I would do the linear regression with v star. Okay, so they are the two unknown of my regression problem. Okay, so the challenge here, if I want to perform this task, is to detect the relevant token and then to fit a linear model. Another way to see this problem, this is a kind of sparse problem, sparsity problem, sparsity, but in a token-wise sparsity, in the sense that you could concatenate all your tokens into a big vector, and you would have to put the component of v star on a particular location so that you can do the proper scalar product in between. Okay? So it's a kind of support moving sparse regression, but sparse in terms of token, not in terms of coordinate. Okay. Exactly. So why did I?
Token, if you concatenate all of them, each token is just a set of coordinates, right? So you have first d coordinate, the next d coordinate.
Exactly. But which one? Among the L possible?
So you need to choose. So it's sparse and there's blocks of d.
Exactly. It's block sparse, and I have L possibility for the support of this V inflated V vector. Okay.
But
So,
even if you, if I can just ask one
Yeah.
question, even if your k star is equal to 0, you can still potentially identify it if your gamma is very different from yours, right? Suppose gamma is much larger than just look for outliers.
why did I put a gamma here? Normally this is for the statistician in the room, because I don't want to deal with a case that is trivial. For instance, so let me write it. So when we look at in expectation the magnitude of my token, what do I have? So when I'm not a relevant token, then I have D, right? And when I'm the relevant token, in expectation, the square norm is equal to D over 2 plus gamma 2. Okay. So it means that for the rest of the talk, I will assume that gamma square is equal to 1/2. So that my relevant token is not distinguishable just by the magnitude of its norm. It would be too easy otherwise. Okay? So I choose gamma square to be equal to 1/2. so that in expectation, all the tokens have the same magnitude, right?
So what happened to K star doesn't appear in things?
Because it's on the sphere.
Oh, it's on the sphere.
It's on the sphere, yes. Unit vector, okay? Okay, good. So maybe let me put here that gamma squared is equal to 1/2, but this is not important, just to have a simple, not a simple case.
You were trying to solve the parameter estimation problem here.
So yeah, so indeed, to perform the regression, we will be interested also in a kind of interpretable model. So I will construct a predictor, and then I will try to convince you that this is indeed an attention-based learner. You have a question?
You're not assuming anything on the sequence of tokens, if it is a Markov chain or anything like that.
On what? On
On the
X?
sequence of tokens?
No, so you see that conditionally on G0, my tokens are independent.
I see.
Okay, they are just wrong according to this distribution. Okay. This is a strong assumption, right?
Right.
But still, it was hard to make the computation. Okay, so let me maybe give an example of why we are looking at this problem. We were inspired by natural language processing. So this is the interactive part of the talk. So let's say that we are given sentences that are made of question followed by answers. Okay? Question plus answer. Okay. We want to predict, so we want to perform sentiment analysis, and we want to predict, to analyze. Yes, yeah, the sentiment in the answer. Okay. So to do so, could you give me, if you don't have any inspiration, it's okay, I have a backup for you. So could you give me like a short question followed by a short answer? I would like, if possible, a good feeling in the question and a bad feeling, a negative feeling in the answer. Okay, short question with a good feeling inside. Do you have any idea?
What's your time at the restaurant? What was your time at the restaurant?
It won't work because yes or no is not really a sentiment for me. Okay.
So good or bad?
Yeah, and so what was the question, sorry?
Was your time at the restaurant good?
Okay, let's take this. Okay. So question and the answer, I would put a negative feeling. This is not what I would answer right now. I hated it, right?
Can I still take a step back and ask
Yes.
something about the model? So J0 is chosen randomly and uniformly at the beginning, and then
No, it changes with each
Every-
word, with
with
each sentences.
with each sentence, and one sentence is this x1 to xl followed by the answer,
Yes.
and for each of them,
Exactly.
and you get samples of this,
As
a
this
bunch of them.
sentences and scores. Yeah.
Right. Okay.
Yeah.
I see.
And G0 is moving.
This- And then, I mean, if it were parameter recovery, then you would like know the minimax rate or some sample
Yes.
complexity of this problem. And is that
You will see that the statistical analysis is quite short in this paper. You will see. I will discuss it. Okay. So here we have x1, x2, x3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10. So I have here all my token, right? 10. Okay. And I will look at the alignment with K star of those words or token. So alignment with K star would be, so K star here is the direction to which my relevant token is aligned. So to be a relevant token for this task, it means that you should contain a sentiment and that you should be in the answer. So was the time at the, this is neutral, there is nothing about this. Restaurant, good, good. Okay, maybe start to align with K star because there is a good feeling inside, but this is in the question, right? So this is not good. Maybe a bit here. Okay. And I hated it. This is a sentiment in the answer, so this should be very much aligned with K star. Okay. Okay, and there we have something.
Sorry, I just want to understand the analogy here. So hate here is kind of like Y and the rest are X, 1 to XL. Is that what you're trying to
No. For the moment, this is just the in sequence.
Oh, it's the whole.
So it's just X1, X2, X3, X10.
Okay, makes
Okay.
sense.
This is just the sentences. And then I check the alignment with V star. So just from this line, I saw that this guy is very much aligned with K star. So it means that this guy is my relevant token. Okay, so here G0 is equal to 9. Okay. And then I look at the alignment with V star. The alignment with V star is there to tell me if the sentiment is positive or good. It's positive or negative. Okay, so no sentiment, no sentiment. Super positive. And here super negative. Okay. So then my prediction, the Y associated with this sentence would be given like this.
So K star itself is not a token, it's some sort of abstract concept.
Abstract concept, exactly. That encode the relevancy of the token for the task. Is that good? Yeah? Okay. So what we like about this, this simple model is that it has two main features. The first one is the token-aware sparsity that you can see in attention-based learning. You see that there are a few tokens that are important for the prediction task in general. And you also have those latent linear projections that are embodied here by V star and K star. Okay. So let me start. So what can we say? We have to construct a predictor to solve this task, and we want to make it natural that it should be an attention-based predictor. So first, what we are going to do is to concatenate, just store the information. So I will put X to be my whole sentences, my whole sentence. This is a matrix of N times T. Okay? So I just store all my words here. Okay, step one. If I knew K star and V star, what should I do? If I knew K star and V star, I would form the following prediction. So I will first compute all the scalar product between my token and V star, and I would select the little G01 that is dependent on my sequence, where G0, little G0x is the argmax of the scalar product with K star. Okay? compute all the scalar product between my token and K star. I select the token that is the maximally correlated to K star. It gave me the index G0x. And then I just check at the XG0x transpose V star. Okay, natural. Okay. So there is another way to write this, to say that you have an indicator function here, that the argmax of xk star is equal to against x v star. Okay. Two problems about this predictor. First, I need to know K star and V star. So in practice, I have to learn them. Second problem, I have this non-differential operation. Okay, so let's relax. We will consider instead this version. Okay. So soft, K, V, and lambda, where we replace the argmax by the softmax of temperature lambda, okay, x, K, and against x, V. Okay, so I replace K star V star by K and V, two parameters, and the argmax by softmax lambda. You see that when the temperature in the softmax tends to infinity, everyone knows what the softmax is? Yes, I can write it. Yeah, it is. Yeah, okay. Yeah, I don't know. Okay. So I put it. So softmax of lambda z is equal to exponential lambda z L over this is a vector that I obtain with exponential lambda z L for each component of z renormalized. So I have a probability vector. So when you take the temperature tends towards infinity here, you retrieve the argmax. So this is a natural relaxation. Okay, and of course, if we stop here, we are stuck in the mathematical analysis that is coming. Why? Because we are doing regression, and I think it's really hard to do regression with softmax using a quadratic risk. So we decided to replace the softmax activation function by the component-wise activation function. So another simplifying step is this one. Here I will use the R function instead of the softmax. Okay? The R function is given. Well, this is something that is f of u is proportional to this. Okay? So if I plot it, this is it between 1 and -1. Okay. So this activation function is nice because when my XL token is aligned with K, I will be in the saturating part here, so equal to 1. This is equal to 1. And when I'm not a relevant token, so meaning that I'm not aligned with K, I will be around 0. Okay. So I just forget about the scalar product of this token with V. Okay. So do I have to convince you that this is a kind of, well, this one is a kind of transform attention-based layer where you can hide the query part in the temperature of the softmax. And you choose your key and value matrices to be row matrices, just vectors. Okay, so I think I will stop the analogy here, except if you want me to be more explicit.
Just one question, softmax has the same property as air, right? So if you're in a line, you're gonna meet to the near one, if not, you're.
Yeah, it has, but this is stronger here. Here, okay. This relaxation works here because in our statistical task, there is only one token that is relevant.
Right.
And because there is only one max in the sequence, this is okay to replace F by softmax. I'm saying this, why I'm saying this is it's because you see that in the F, we do not have any renormalization. Okay, so it's just that 1 is equal to 1 in a certain sense. Here there is a token that conveys all the information. So my softmax is actually a 0, 0, 0 and a 1. Okay. But if you have like more complicated structure, like several tokens, you would need a second head of attention. And things are not so nice. We can discuss about it.
So basically, the way we are going, actually, you're just focusing on one layer, right? So
Yeah.
Yeah. So you're saying that one layer is enough actually to do this.
Yes, to do this, exactly.
And you don't need even MLP, you just need like attention. Oh,
I don't need.
MLP, right?
No,
Basically,
I
it's
forgot about the NLP. And okay, so indeed, for people that know about attention, so normally attention layer takes a sequence of token and output sequence of token. But here, people also in practice would use like an artificial token before the sequence of the input sequence. They call it CLS,
yeah.
And they will store the regression here output in the CLS token. So in the input, there is nothing in this artificial token, but once you do the attention layer, you can retrieve the regression output in this token. It's just an implementation trick to perform regression with an attention layer. Okay.
What is lambda, the analogous of lambda?
Lambda, you have lambda in attention. This is the temperature of the softmax. You have it. And you have to know how to tune it actually when you train attention layers. So this is an extra hyperparameter of the. Okay, are we good? So let me now try to give you a bit of the statistical analysis that we have done. But you will see that the statistical analysis is quite short because this is hard for us at least.
Well, there is no algorithm yet, right?
No algorithm for the moment.
I see.
Then we will do training at some point, but for the moment we are just looking at the statistical model. I think. So about statistical optimality. So we look at the risk, okay? So quadratic risk. And what I will return with my F attention-based learning. Okay. First observation. You know that for the quadratic risk, the optimal predictor, the Bayes predictor, is the one given by the conditional expectation of y given the input. Okay. So the first observation that we could do is to try to compute the Bayes risk for this task. So the Bayes risk could be this one. Okay, but we don't know how to compute this. What we can say quite easily by Pythagorean inequality is that this Bayes risk is larger than this one. If I mu G0. Okay? And this is just the expectation of the noise square. That I will call it epsilon square. Okay? So we don't know how to compute the Pi's risk, but we know how to lower bound. Then I will make the following assumption that K star and V star are orthogonal. This is just to make easier computation. There is nothing deep about this assumption. Okay. And I have the following proposition. So in an asymptotic regime, when the dimension of the embedding tends towards infinity, the length of this input sequence is a little OD. So it can be fixed, but it can also grow towards infinity, but not too fast. If I have lambda square root of d that tends to 0 and lambda square root of l that tends, sorry, inverse, plus infinity here, 0 here, we have that the risk with of our predictor with the optimal, the oracle, sorry, not the optimal, the oracle parameter will tend to epsilon square. So it just means that here, if I plug K star V star, the one that are determining my my statistical model, I plug it in my predictor here, and in an asymptotic regime, this predictor would be optimal.
Wait, just a second. So lambda is your
The lambda is the softmax temperature.
so you're increasing that as well.
Yeah. I need to do it. Why? You see, I need to do it because when lambda tends to infinity, I retrieve the argmax kind of argmax property. Okay.
Right, but why lambda the square root of L should go to 0? That
Oh, why I have those property here? Yes, so let me just comment. So I finish the oracle predictor. So T lambda K star V star, sorry, is asymptotically Pi's optimal. Okay? And so now you ask about why those scaling are appearing. This is
just to make sure. So L is also going to infinity, right?
it could be fixed, but it has to go to but it has to, if it goes to infinity, it has to go slower than.
But it also has to go like. So because lambda square root of L is also going to 0, so it means that lambda should go to infinity like way faster than.
Yes, but
So the other way around.
Yeah.
How's that thing is going to 0? It's,
lambda square root of L.
yeah.
So what you can choose is
Exactly 1 over L.
yes,
Oh.
Because L is much smaller than D.
yeah. So those things are appearing just because when you took this predictor and you separate what happened with for the G0 token and what happened for the rest of the sum, and you will see those scaling appearing. I mean, this is really just about computation. It's nothing deep.
So this is just saying that like if this is a realizable model, you have some K star D star. So it's just saying the base risk of that K star D star is actually like those are.
It's just saying that
realizable for.
apparently in an asymptotic regime, the byte risk is epsilon squared. But when you have fixed dimension, we don't know how to compute the byte risk, and we don't know how to show that this is a good idea to look at this predictor with K star V star. This is only.
So this predictor is not used here.
It is. Look, the definition of the risk here is for the predictor, the R predictor. And I'm just plugging
Okay, so if
K star
you-
V star,
I see.
okay?
So if this predictor is with K star V star,
Yes.
then,
The oracle predictor. I take my predictor with oracle parameter.
okay,
Okay.
But the first one, that one, the expected value of y, yeah, that one is just equal to epsilon squared, no?
You think so? Or if you manage
No.
to show it, I'm curious.
It's not obvious.
Uh,
Because the
of
optimal
course.
predictor would be, like if you are in, if you know what your J naught is,
Yes.
then you just predict, right? Like this is the
Yes.
this is the expected value.
No.
Why is it not equal, I guess, to this? Well, because I guess, to me, it seems like it should be equal, no? Maybe I'm missing.
No, I don't know, but because if I give you an input sequence, how do you know which one is the token, the relevant token? I mean, this is
Right, no,
Right.
because you don't have this kind of oracle access to
No.
this thing. Even the best predictor will not have oracle access. I
Yes.
see, okay.
yes,
Excellent.
and we can do a sanity check and compare with what happened with the linear model. Stay a long time, so I keep this. Maybe I should put it on this. No.
It's probably okay not to do it.
Okay, not. I trust you. Let me just put here. So I keep just my predictor, okay? And I remove. So what about the linear model? This is just a sanity check. Imagine that now we focus on beta star, which is the R mean of a big vector that the R mean, sorry, of the quadratic risk, but where you concatenate all your tokens into a big vector. Okay, so you do like standard linear regression by concatenating all your d-dimensional vectors in one big dl dimensional vector. You can run all the computation, and the risk of this beta star will be given by this expression. Okay, when G0 is uniform among all the indices. Okay, and so we see here that in an asymptotic regime, when the length, for instance, of your sentence tends to infinity, this tends to epsilon squared plus gamma squared. Okay, and this is a risk of the null predictor. You can show that this is the risk of the null predictor, the one that is always returning 0. So it means that when the length of the sequence increases, your linear model is completely out. He's as good as a null predictor, so he's not learning anything, and it's because he has to put information a bit everywhere since the relevant token is moving, but by putting information everywhere, it drowns the whole information.
But the expectation is also over J0, right?
J0 is it's hidden in the distribution of this sequence, right?
Yeah, and the expectation also includes that, right? It's over the randomness of J0.
Yeah, sure. But sure. But I don't give J0 to this model.
Yeah, so there's no way that one method can.
If L is equal to 1, then I retrieve epsilon square. N is equal to 1, but it's somewhere because here, if I have only one word in my sequence, this is the one that is relevant, and this is linear regression. Okay? Okay, good. So linear models are out here. This is the end of the statistical story. Now we can do a bit of training. Okay? And we go back to a setting where we are not in an asymptotic regime. Okay? We are back to finite dimension, finite length. That's okay for everyone? Let me.
Just one second.
Yes.
The linear model thing, so beta is just a d-dimensional. I'm just trying to
DL.
DL.
I put all my tokens here as a big.
Oh,
Big
a
vector.
big thing.
Yeah.
I see.
Okay.
So what if I put some regularization?
It will be the same. You could put lasso if you want. The thing is, the support of the relevant token is moving from sentence to sentence. So even if you put block sparsity, it won't help.
Okay.
Okay. Okay. Like this and try to give you in 5 minutes the end of the story about training. Okay, now I think I will try. Sorry, Misha. So now we want to understand if we can learn those parameters. Okay. So about the learning, what we are going to do is it's not exactly training, particular training, even if it's considered in the literature this way. So we will show that, spoiler, gradient descent recovers the Oracle parameter. So K star, B star. Okay. So to do this, so recall that we have our risk, so I will write it here. Our quadratic risk. Okay, and we will do training. So I put quote on training. Yeah, minimization of the theoretical risk. Okay, so this is not exactly training because in practice I would have samples and I would minimize an empirical risk. But we perform training this way.
Sorry, it's on what? So what is?
I will directly optimize this function. Like if I have access to the gradient of this function. Okay.
So it's not about the attention yet.
Sorry?
It's not about the transformer at all.
It is because here I have my transformer based predictor.
Oh, that's his. Okay, I see. Yeah.
Okay. So this is. So even if I'm looking at the theoretical risk instead of the empirical one, this is still a non-convex problem. So this is non-trivial to optimize. And training will be done by projected Riemannian gradient descent. What do I mean? I mean that my iterates kt plus 1 will be equal, to projection over the sphere of kt minus the step size identity minus kt transpose of the gradient in K of my theoretical risk lambda kt bt. And the same for bt, for bt plus 1. Okay, you just replace kt by bt. Okay, so this is a projected gradient descent, projected Riemannian gradient descent, So projected, this is natural because I made this assumption. And here you see that we have the gradient of the risk that we want to minimize, but with a projection over the tangent space of the sphere, at KT. Why do we have this? It's because we are able to compute this risk only over the double sphere, not everywhere in the space. Okay? So since we only have access to the risk over the double sphere, we need to do like a proper gradient descent. Okay? And this is a precaution that you need to take. Okay, yes.
Is there a retraction map for this?
It's tractable.
Retraction map, given that you're using Riemannian grid.
What is tractable? This?
Yeah, or like, I mean, after the projection, how are you coming back to the grid?
I don't come back to the. I don't get your question.
It's not really, I mean, what is the projection over here?
The projection for me, okay. We have two constraints. Yeah, it's just a renormalization. Okay. So the gradient step, this is a projected gradient descent, but just in the gradient descent, here in the gradient step, I perform it by a projection over the tangent space of the sphere. It's because this risk is empty. I don't write it because it takes the full whiteboard. And we only have it over the sphere. Okay, so what we realized when we look at those iterates is that there exists a submanifold. I will define it just right now, and I will. To define the submanifold such that KB lived on the sphere and K transpose V star, K star transpose V, and K transpose V are equal to 0. Okay? We have the three scalar products that are equal to 0. If KT, VT belong to this submanifold, then KT plus 1, VT plus 1 stay in this manifold. So it means that this submanifold is invariant for my PGD iterates. Okay? Of course, you see that this submanifold requires the knowledge of K star, V star. Once you have understand this about the dynamic of our PGD iterates, we are able to show the following result. You take lambda T, the temperature, to be constant over time. There exists alpha bar such that for every step size alpha less than alpha bar, and for a generic initialization of my PGD iterates K0 V0 on the invariant submanifold, I have that KT VT converge towards K star V star up to a sign. Okay, so it means that to show this, we have to study the optimization landscape. So when we initialize on this submanifold, we stay on this submanifold. We can reparameterize the problem by all the scalar products possible of K, the alignment of K with K star, the alignment of V with V star that you want to converge to 1 or -1. The alignment between K and V star, K star V, and K and V if you kill here those scalar products, then you depend only on two scalar products, the alignment of K with K star and of V with V star. And you study the critical point of restricted to this domain. And you will see that there is some saddle point, but you can escape them. Okay. And you will converge despite the non-convexity towards the local minima that are global here. And this is up to a sign, but we don't care because if we put minus and minus here, we retrieve the same prediction, right? So up to a sign, I have discovered the right direction. Okay.
I'm not sure what the claim exactly. This is in the product or is this?
This no, this is just the each one.
Each one converges to that one.
Yes.
So the theorem is that it converges to something.
It converges to the oracle parameter.
To what?
To the oracle parameter. The
Oh,
one,
to the oracle parameter.
Yeah. The one that are.
Oh, the K star. Oh,
Yes,
okay.
K star, K
I
star.
thought it was infinity.
No, K star, sorry.
See, okay.
K star, V star.
See.
Okay.
So the initialization condition is still pretty strong, right? So
Yes.
you have to be on-
You're right. Yeah, you have to be on the manifold. So it means that you have to do K star, V star. So in practice, what we tried a numerical experiment where we were not on this submanifold. Before doing numerical experiment, we tried to show that this submanifold was stable, meaning that when you are close to it, you will be attracted by it. We didn't manage to show it theoretically, but empirically, we see that you can have such a nice behavior because when you initialize randomly over the sphere.
So did you see the trajectory that it is? Like suppose you have a random initialization.
Yes.
It actually go to this manifold?
So exactly. So if you initialize randomly over the sphere for K0, V0, at the beginning you are close to this manifold. You are not on this manifold, but you are close to this manifold. And then if you want the optimization to go well, you have to play with the temperature. And you have to make this temperature move to have like nice convergence properties. So it means that if we really want to show that this submanifold is stable, we have to do like a more finer analysis by making those hyperparameter moving. And we have done it.
So this softmax and the error function, they are actually pretty like the probit and the logistic.
So logistic is 0, 1. So it's important to be in 0 at 0. Because I want here, you see, I want that when I look at scalar product between a non-relevant token with K or K star, I want it to be close to 0 so that there is no contribution of it in the output. Okay.
You do this approximation so that gradient you can actually compute with this error function. Like
Yes.
Much
Yes,
more manageable.
exactly. You have a nice compatibility between the R function and the Gaussianity of your token. That's why we are able to compute this risk. Yes, if you change here the activation function, we don't know how to run the computation. Yeah. So I agree, this is a bit frustrating because we would like to have a stronger theoretical physics saying that if I initialize everywhere on the sphere, everything should go well, but this is actually a bit much more trickier. There is a second thing, we perform a lot of numerical experiments, and a Blackboard talk cannot pay tribute to this. But we also try to over-parameterize K and V, like using matrices instead of row matrices. And we see that it goes well in the sense that if you look at convergence at the first principal component, the first eigenvector of your matrix or matrices, you retrieve K star, V star. And then the story is much more complicated if you have now two tokens that are relevant. Okay, if you have two tokens that are relevant, then you would say, okay, I can put two attention heads. one with K1B1 and another one with K2B2. But here we see that in the numerical experiment, both heads learn a mixture of the model across the tokens. So we would like to have like interpretability completely, meaning that we would like that each head is able to capture only one token, but you need to do something more to have this nice picture appearing.
So, so instead of like you have the tangent sphere over there for Riemannian GD.
Yeah.
Can this be? Can you change your loss function in a way so that
But then it won't be.
the L2 loss?
Yeah, L2 loss, but we are doing regression here, so I don't know what you. I
So
mean,
what I have in mind is I just want to analyze gradient descent. But it seems like you cannot find the manifold that like so that KT plus 1 will be in the same manifold after one gradient state. If I don't have that correction, the tangential sphere thing, with this loss, right? So that would be gone. So therefore, what I
okay, this is just for the mathematical analysis. This is just because we don't know how to compute this risk everywhere on the space, on RD times RD. We only know how to compute it on the sphere times the sphere. Okay, so this is why we need this.
Why cannot you compute it everywhere?
Because this is tough computations.
But what if you allow K and V to be not norm one?
Yes, so not on the sphere, yes.
Then I think it only becomes easier, right, to compute the risk.
No.
What's the problem?
So it would be something complicated and they can only compute the projection on that sphere in some sense.
I think you will have several issues. One is the scaling. Okay.
So there is some indeterminacy, right?
Yes.
You can multiply one and
Exactly.
divide the other one, yeah.
Exactly. And yeah, it's just.
But that